So I'll speak about gravitational collapse to extremal Reissner-Nordström and the third law of black hole thermodynamics. And so let's review very briefly black hole thermodynamics. So this is a proposed close mathematical analogy between classical black hole dynamics and classical thermodynamics, and it was put forward by Bardeen, Carter, and Hawking in this influential paper from 1973. And basically, it states that the classical laws of thermodynamics have analogs for black holes. And the first law, which is actually labeled the zeroth law of classical thermodynamics, states that temperature is constant in thermal equilibrium, which in the black hole case translates to the fact that the surface gravity is constant along a stationary horizon. The first law is a type of energy conservation in classical thermodynamics, and the black hole's case as well. The second law is maybe the most famous one, is that the entropy is an increasing function of time. And in the black hole case, it's just that the area of a black hole can only increase. And the third law states that in classical thermodynamics, temperature can never reach absolute zero in a finite process. So it's the unattainability law. And in the black hole's case, it states that the surface gravity kappa cannot reach equal to zero in finite advanced time. So the first three laws have been suitably interpreted, proved by Hawking, Carter, and Wald. Whereas the third,
there's a question by Tzvi.
Oh, there is a question.
Yeah, I must make an historical comment.
Yeah, please.
The paper that Hawking, Carter, and Bardeen wrote, this Bardeen, Carter, and Hawking, was to disprove the analogy. The whole purpose of the paper and the spirit of the talks that they gave on this paper was that there is analogy, but there is no black hole thermodynamics. This was done. I'm probably the only person old enough here to remember this time. So their point was, yes, there is this analogy, but to talk about black hole thermodynamics is nonsense.
Okay, that's interesting. I mean, are you you mean this paper here?
That's why they call it mechanics, not thermodynamics. They say, yes, there are these three laws. There is miraculous coincidence, but this is not thermodynamics. So historically, people, Bekenstein at that time was the only
רק שנייה. לוי?
סליחה?
Okay, so that's interesting. Okay, I mean, if I read the paper several times and it wasn't so clear to me, so thanks for clarifying this. Yeah. Okay.
Yeah, you can add to that the fact that when Jacob Bekenstein actually suggested that,
no, this was before, right? Yeah. So I know also, of course, his paper. Yeah. Yeah.
No, but the point is that Hawking tried to disprove this idea, and that's why he wrote this paper. And this I heard personally from Jacob.
This is just what I said. This is what this whole paper is about.
Okay, well, thanks for clarifying this. So by reading this paper, it wasn't so clear to me, but yeah. Okay. So I will maybe go on and okay. So in my talk, I only talk about the third law, which they actually also state as a conjecture, which I can also come back later. Okay. So, but before we talk all about this, let me just refresh our sort of set the stage by introducing the Schwarzschild solution, which I've depicted here as its Penrose diagram. And we can think of Schwarzschild as arising as the maximally Cauchy development of space-like data, which are sort of topologically R cross S2. And so we also know that the exterior is foliated by untrapped spheres and the interior foliated by trapped spheres. So this means that the sphere is trapped if both future null expansions are negative. And even though sort of the full Schwarzschild solution does not arise in gravitational collapse, from data on R3 because it had the sort of Cauchy hypersurface has a rather different topology. It is still important in the question of gravitational collapse, as can be seen by looking at the Oppenheimer-Snyder collapse picture, in which actually a fluid is collapsing, and in fact the exterior is, by the Birkhoff's theorem, isometric to a piece of Schwarzschild. And in fact, sort of that piece of Schwarzschild, which is to the future of such an incomplete slice, is actually isometric to the piece here arising in gravitational collapse from one-ended data. So the point is that even though the full Penrose diagram does not arise in gravitational collapse, part of it do. Going now to the sub-extremal Reissner-Nordström family, a solution to the Einstein-Maxwell system, the Penrose diagram looks like this. And in addition to a black hole region, so we have the exterior black hole region, and then we also have these like further regions here, and those boundaries are denoted by Cauchy horizon. And again, by looking at an initial data slice of this type, the unique future development is now determined up to exactly this boundary called the Cauchy horizon. But on the other hand, you can also look at incomplete data of this type, where where the initial hypersurface penetrates also that regions behind the Cauchy horizon, and as long as you don't go too far towards r equal to 0, in particular that as long as the radius is greater or equal than e squared over 2m, then the Hawking mass of all of those spheres of the initial data is in fact non-negative. So those spheres can, in principle, arise from gravitational collapse of one-ended data. I should note that spheres closer, smaller than this radius here, they cannot arise in gravitational collapse because they would have negative Hawking mass, and one can prove that the Hawking mass has to be always greater or equal to 0 in spherical symmetry, at least. And okay, so in terms of trapped surfaces, it is rather interesting now that, well, again, you have this untrapped region, we have a trapped region here, but beyond this Cauchy horizon, the spheres are again untrapped. So there, in the interior, there are solutions, there are spheres which are untrapped. If we now go to the extremal case, in which case the absolute value of E equals to m, then the Penrose diagram looks like this. And again, one can either look at sort of complete initial data, which in fact now is also to the left geodesically complete. And then we only get the exterior region, but to also have some sort of interior patch, we can look at the slice of this type, which again is incomplete. And as long as we don't go too far into the black hole towards r equal to 0, as long as r remains bigger than m over 2, all of those spheres have a non-negative Hawking mass, so they can arise in gravitational collapse. And in fact, we actually proved that any such sphere can arise in gravitational collapse. So in terms of trapped surfaces, it is rather interesting now that the interior here is completely untrapped. So there do not exist trapped surfaces in the interior, and of course the exterior as well. And only the event horizon is folded by marginally trapped spheres. And if we now take the value of the charge to be bigger than the mass, then we get the super extremal Reissner-Nordström solution. This is not a black hole solution, but rather an eternal naked singularity, and has a Penrose diagram of this type. And it looks like Minkowski space, except that r equal to 0 is singular. So nevertheless, even though the full Penrose diagram cannot arise in gravitational collapse, and you cannot have especially this sort of naked singularity at r equal to 0, as long as you don't go too far in, and r is again bigger than this, then all of those spheres can in principle and do in fact arise in gravitational collapse, and are seen as sort of for me now, I define them as physical spheres, whereas the spheres which are smaller than this, they do not arise in gravitational collapse and are physical. So maybe one of the takeaways here I want to stress is that even though So it can happen that part of the space-time is super extremal, but this does not mean that actually the whole space-time is super extremal. So only that when you know that part of the space-time is super extremal, it does not mean that you have a naked singularity. Okay. So to make the third law a bit more precise, or that conjecture is that we have to introduce a surface gravity. And in fact, in the case of the Reissner-Nordström black hole solutions, where E is less or equal to m, the surface gravity, which according to black hole thermodynamics is proportional to temperature, has exactly this expression. And the point is that if it is the black hole is sub-extremal, then it is positive, and if it is extremal, then actually it is equal to 0. So the original formulation of Bardeen, Carter, and Hawking, and at least in that paper, if you read, then it says that it is impossible by any procedure, no matter how idealized, to reduce kappa to 0 by a finite sequence of operations. So this is lifted from their paper. And actually this formulation was later revised by Werner Israel in this paper, Third Law of Black Hole Dynamics, a Formulation and Proof. And so in my abstract, I wrote that I provided a disproof of the third law of black hole thermodynamics. And here this paper states it has a proof. So there is obviously some contradiction here, and I will address the issue also about the proof of the supposed proof of the third law. But first, I would like to address the issue of a more precise formulation of the third law, which was put forward by Werner Israel. So he writes that a non-extremal black hole cannot become extremal, I lose its trapped surface, at a finite advanced time in any continuous process in which the stress energy tensor of accreted matter stays bounded and satisfies the weak energy condition. So there's lots of words, so I would like to go slowly through that statement. So the finite advanced time replaces now the rather vague finite sequence of operations. Any continuous process states that, well, this is fundamentally about the non-generic behavior. And indeed, Bardeen, Carter, and Hawking and Israel knew that adding the word generic would make it triviality, which does not even use the Einstein equations. The stress energy tensor stays bounded. This is a regularity condition. And if singularities were allowed, counterexamples have been produced using massive dust shells. And the weak energy condition must be enforced. Otherwise, you can also provide counterexamples. So the conjecture, a bit more precise, the third law, which was written in Bardeen, Carter, and Hawking and reformulated by Israel, states that a sub-extremal black hole cannot become extremal in finite time by any continuous process, no matter how idealized, in which the space-time and matter fields remain regular and obey the weak energy condition. So our result from 2 years ago, together with Ryan Unger, states there exists a precisely defined process in which a sub-extremal black hole becomes extremal in finite time, evolving from regular initial data in the Einstein-Maxwell charge scalar field system. So in particular, the third law of thermodynamics is false. And before I'll give you sort of the proof of our result, I would like to address first the issue of the paper of Israel and sort of what's wrong with this proof and what actually his argument shows. So his argument is in my opinion a very nice argument, and it's very elegant, and it's easy also to present. So he argues by contradiction. So assume that first an incoming matter flux creates, so this is now about spherically symmetric black holes. So we have this sort of, we can visualize them nicely as a Penrose diagram. So first assume that this matter here, this big matter flux, creates a sub-extremal apparent horizon here, or outermost apparent horizon here. And then later a second matter flux pushes this outer horizon to extremality, and this is now an extremal horizon. So suppose this happens. So this is exactly what is meant by a sub-extremal black hole becomes extremal in a dynamical context. So let's zoom in a little bit where the action happens, namely here. So now he uses two statements. The first statement is, by the energy condition and Reissner-Nordström's equation, trapped surfaces persist in evolution. This means that if you have a trapped surface here, therefore for any advanced time b bigger than that advanced time, you also have a trapped surface. And so in particular, this also applies to marginally trapped surface. So this means that every sphere for bigger advanced time than this outermost apparent horizon is also marginally trapped or even trapped. So everything here is marginally trapped. So the second ingredient he uses, that if you remember that extremal horizons, they have a neighborhood around them which is free of trapped surfaces. And also actually the neighborhood is also free of marginally trapped surfaces except for the horizon itself. So now these two are in contradiction because one says there have to be trapped surfaces behind here or marginally trapped surfaces.
Christoph, question.
Yeah.
So what do you mean persist in evolution along
So this, I mean that, okay, in spherical symmetry, you have this nice double null foliation. And for any advanced time v bigger than the one, so if you have a trapped surface here, then every surface to the right along v bigger than along the constant u has to be also trapped. Okay, this is just a consequence of the Reissner-Nordström equations.
Okay, so along evolution along an outgoing null geodesic.
Yeah, null curve. Yeah, but yeah.
Okay.
Yeah. Along and outgoing. Yeah, exactly. Yeah. So this does not apply to ingoing, but to outgoing. Exactly. So this means that, okay, since everything here is marginally trapped, everything behind here to the right also has to be marginally trapped. Okay. So using those two ingredients, the horizon cannot be extremal. So I think it's a very pretty and easy argument. However, there's an implicit assertion in this argument, namely that regular solutions, they have a connected outermost apparent horizon. In particular, that in this diagram, this actually is connected and doesn't break somewhere. And this assertion is actually that he makes this assertion is also clear from what he writes, namely that infractions can result from the absorption of an infinitesimally thin massive shell, which forced the apparent horizon to jump outward discontinuously. So he associated sort of discontinuity or disconnectedness of the outermost apparent horizon to irregularities of the matter model. But this is not right, namely that generic horizons or outermost apparent horizons do not have connectedness. Okay, so apparent horizons can jump in smooth spacetimes because they're defined through a level set, and smoothness of the spacetime does not mean that the apparent horizon is connected. And in fact, for generic spacetimes or generic solutions, you don't have connectedness of the outer apparent horizon. So
I asked about this. Can you elaborate? I don't understand what you mean by disconnected apparent horizons.
So I think the next slide will maybe clarify this.
Okay.
And then if it's not, then please ask me again. So let me now present our counterexample of the third law. So we look at fine-tuned Cauchy data for the Einstein-Maxwell short-scale field model, sort of post on R3, which undergo gravitational collapse. And we tune them in such a way that first we form a sub-extremal Schwarzschild apparent horizon here. So this is actually isometric to a Schwarzschild. If you want, we can also make it sub-extremal Reissner-Nordström. And then later, the outermost apparent horizon actually looks like this, and then it jumps here outwards, and then you have an exactly Reissner-Nordström event horizon later. Our solutions are arbitrarily regular, so for any k there exists ck examples, and it also satisfies the dominant energy conditions, in particular the weak energy condition. And here you see that the apparent horizon actually jumps. The outermost apparent horizon actually jumps. And this is what I meant by disconnected apparent horizon. So it consists of those two connected components. And the outermost apparent horizon becomes disconnected actually the instant the black hole becomes extremal. And this happens here. So if this is sort of the reinterpretation of Israel's argument, actually, what it shows is that actually the outermost apparent horizon has to become disconnected the moment it becomes extremal. And this is a feature and not a glitch of the matter model.
But
yeah.
What is the physical process that actually leads to this picture?
So what we do is we send in pulses of scalar field in a certain way to first create a subextremal black hole, and then we send in more to then create an extremal black hole. And we tune them in a certain way to do exactly what I just told you. I mean, is that what you're asking?
Yes, that partially answers that. For example, how much energy do you need to put in these pulses? Is it a finite fraction of the black hole mass?
So actually that's a good question. And okay, I will present now actually how we do our construction. Okay. But let's look at the interior for a moment and keep in mind, of course, that again, so if this is the outermost apparent horizon, so there in the interior we have those trapped surfaces, and then also we have this untrapped surfaces, and here the exterior is exactly q equals to 1, and here, or like q being the charge to mass ratio, and here actually we had the Schwarzschild case, so this actually is q equal to 0. So this is a subextremal horizon, and this is an extremal horizon. So the outermost apparent horizon becomes disconnected, yet the spacetime is as regular as you want. Trapped surfaces persist for all time. And so a natural question is also, if you tune your data not to have an exactly subextremal horizon, exactly extremal horizon here, but a subextremal horizon, what happens to the trapped surfaces, right? Where do they go? And if you now exactly do this construction where you have this subextremal horizon here, which we can also do, and you say that this charge to mass ratio is 1 minus epsilon, and then you want to entertain what happens as epsilon goes to 0. So as long as epsilon is positive, you always have those regions of trapped surfaces just behind the horizon. And as you make epsilon smaller, and smaller, exactly as you hit epsilon equal to 0, you hit sort of these regions of trapped surfaces actually coalesce on the event horizon and in fact become marginally trapped surfaces. And then you get the picture, what I showed you before. And now you also have this neighborhood free of trapped surfaces. Oh yeah, please.
Is your scalar field massless or is it massive?
So we can do it both with massless. We can also do it with massive, but in the massive case, we have to take the mass smaller than the charge. As in like the coupling constant of the Klein-Gordon mass has to be, in fact, much smaller than the coupling constants of the charge of the scalar field.
Did you say mass smaller than the charge?
Yes.
And can you remind me how this relates to the weak gravity and these conjectures? Is it the opposite way? You remember?
Well, the weak gravity states, I think it's consistent. I mean, okay, I don't want to comment on those conjectures, but so somehow the electrons are much more charged than mass.
Okay.
But okay, I don't want to comment on the conjecture.
But won't you get a situation in which the shell, as it collapses towards the black hole, you will get that the electric field in the shell are too large, and you will begin to create pairs, and just like the situation which is equivalent to pair creation in a Schwinger field, in when the charge is too high, when you have too large electric field. And so the collapsing shell will discharge while it is falling onto the black hole. And you won't be able to put as much charge as you want because it will not be carried towards the black hole. Did you check this?
I mean, okay, so this is a solution to the Einstein-Maxwell charge-scalar field system. Okay, so it takes into account the full Maxwell's equation, but it is not, I mean, regarding, let's say, is that like a quantum phenomenon? What you're...
What I'm saying is that when you consider these considerations of thermodynamics of black holes, you have to take into account quantum considerations at times. So there's a whole history of evading the second law, which was shown not to work when you took into account that we live in a universe with H bar. And there was a whole list of debates between Bekenstein, Wald, and Unruh, and so on. So,
I know. Okay, I
so
see
you
what you're
cannot
saying.
say H bar. So what I'm saying is the following, that my guess is that if you take into account the fact that that you can have pair creations inside this collapsing shell, you will be in a situation. This is just what you mentioned, that the mass of these particles is very small, and because of this, it will be very easy to create pairs. And if you create pairs, then the positive charge part of them will escape to infinity. The negative one will stick, and this will reduce its Q, and eventually you'll get Q less than 1. This is my conjecture.
Okay, yeah. So I should say that, so everything I'm going to talk about is in the realm of classical relativity.
Yeah, but we know that even the second law does not hold in the classical limit.
I know. Yeah, I understand.
But I guess a follow-up question on this is: does the electric field become very large at any point?
Yes,
the electric field. The electric field is like the charge equals to mass. I mean, F, the field stress tensor, is like Q. It doesn't become. I mean, it's like the mass, right? Because it has to be. It has to be extremal. So it is of the same order as the mass. So there's no divergence of the electric field. I should also say that everything I'm saying is classical, and maybe I want to stress that the formulations in the statements given by the Bardeen, Carter, and Hawking paper, and also by Israel, were statements about classical relativity, and also everything happens, of course, in a compact domain, in the sense that after finite advanced time, you hit actually the extremality here. So once you sort of think that, okay, well, we know that quantum effects are perturbative on compact domains. So this means that, okay, classically, you will have this extremality, and every perturbations you do can only be at, of course, sort of philosophically at order H bar. And okay, what happens then for a very long time? I agree, this, okay, is open. But I think what this tells you is that you have to face the reality that you become H bar close to an extremal black hole. I think that's my interpretation. But okay, I don't want to go too far because this is the world not of mathematics anymore, so more of interpretations, and maybe we can discuss after the talk. Yeah, but I'd be happy to. Okay, so what happens as we send epsilon to 0? Well, then this happens, but actually we can sort of even continue the process further and not only sort of glue to this cone, which is the sub-extremal horizon, extremal horizon, but rather a super extremal sort of outgoing cone. And in which case, sort of if this part is actually isometric to a super extremal patch, in which case what happens is that the event horizon now jumps inwards discontinuously. So here epsilon is equal to 0 for every non-zero epsilon negative in this case. The event horizon, yeah, 1 plus epsilon, Q equals 1 plus epsilon, the event horizon jumps inwards discontinuously. So at extremal horizons, there is a certain instability of the event horizon.
What do you
mean
mean jumps discontinuously?
So-
What is the parameter that changes discontinuously? And
Okay.
if the derivative is infinite, what does it mean?
So first of all, you parameterize your initial data by this parameter epsilon, which is the solution you're creating such that this part here has charge to mass ratio being 1 minus epsilon, okay? So this is the parameter, okay, it's rather abstract now, but this is a parameter you can choose in your initial data. You should think of it as sort of the total charge if you want, okay? What you can do is that you can change this parameter continuously in your initial data, and that's fine. And what happens is that as epsilon is equal to 0, your parameter, you have those exactly extremal horizon. But the moment you make epsilon a little bit bigger, or like, okay, you make, in other words, you make the charge to mass ratio of this patch of the solution a little bit bigger than 1, then this becomes isometric to super extremal, and the horizon, the event horizon defined teleologically, actually jumps inwards as a function of the u. So if you think of having a double null coordinate system here, on which you put in your initial data, and then you measure the u value, sort of the retarded time, like the retarded time value of the location of the event horizon, then that is discontinuous as a function of the initial data. And this happens exactly at sub-extremal, sorry, this happens exactly at extremal black holes, and it cannot happen for sub-extremal black holes.
Excuse me?
Yeah. Yes.
What happens to the temperature in this case?
So the temperature, okay, if you, so I don't want to think about, I want to stay in the realm of
The K,
classical realm, so exactly K. So it turns out that K actually, okay, sorry, in this case is K is equal to 0. And now once it has jumped inwards discontinuously, it could either be a sub-extremal horizon or again a extremal horizon. Generically, it will be a sub-extremal horizon, in which case the temperature actually also is discontinuous. Yeah, so it will be positive, let's say generically, and it can actually make large jumps. Okay.
Okay, thank you.
You're welcome. Yeah. So this is actually a sort of a critical behavior, that the event horizon jumps inwards the moment the exterior becomes super extremal, and there's no naked singularity. And this event horizon jumping is associated to extremal horizons, and the stability of local critical behavior was already observed by the firm, or conjectured by the Rudniansky Taylor. Okay. Let me also sort of aside something, which is from the original paper of Bardeen, Carter, and Hawking, in which they say that another reason for believing the third law is that if one could reduce kappa to 0 by a finite sequence of operations, then presumably one could carry the process further, thereby creating a naked singularity. So they were afraid of creating naked singularities, sort of in the spirit of the super extremal solution, once you had once you can go all the way to extremality. Sort of in so this has been going on for a while, and it's called sort of overcharging or overspinning of black holes, but this is a doomed endeavor, and you can actually disprove the possibility of overcharging in spherical symmetry, and this has been done already 10 years ago. And sort of only because part of the spacetime is isometric to super extremal Reissner-Nordström does not mean in any means that there exists a naked singularity. Okay. So, well, the Einstein-Maxwell charge-scalar field system is this system we all know and love. The Einstein equations coupled to electromagnetism and a charge-scalar field. So here, actually, I'm only looking at the massless case, but you can also add, as I said before, a small amount of mass here in the Klein-Gordon equation, or in the charge-Klein-Gordon equation. And so to present the proof, I would like to introduce now an easier version of it. And first, the uncharged scalar field model, the Einstein scalar field model in spherical symmetry. And you should essentially think that, well, those are wave equations for the scalar field and the radius r, and also the lapse function omega squared, which in spherical symmetry, we can write a metric like this. And then we have the Reissner-Nordström equations, which you should think of constraint equations on null hypersurfaces. And of course, we have also the propagation equation of the Hawking mass. So I will now sort of present an easier problem in which we actually want to create a Schwarzschild black hole with a prescribed mass. So later we want to create an extremal black hole with a prescribed mass and charge. And now first I want to present the easier problem of creating a Schwarzschild black hole, and which sort of after some finite advanced time is isometric to a Schwarzschild solution with a prescribed mass. And to do this, we use a certain technique called characteristic gluing. So you want to have a patch of spacetime here and then glue it along a null hypersurface, in which case, of course, this should be coincide with the event horizon. This is our favorite null hypersurface in the case of this problem, and to obtain then a Schwarzschild exterior. So the goal is to set up characteristic data on this part between this Minkowski sphere and this Schwarzschild event horizon sphere, such that well, the radius and the masses both are here specified, and moreover that the scalar field is identically zero there and identically zero there, and moreover all tangential and transversal derivatives of the scalar field are zero here and zero there. So this is the goal. And once we have done this gluing, then we can actually locally solve this characteristic problem a little bit to the past, and then obtain our solution, our Cauchy data, if you like, Cauchy data, sort of by just using the imposed data on a space-like hypersurface. So this actually is while everything reduces only to understanding the solutions along sort of this finite cone. So our theorem,
Sorry. Question. So after you make all these demands from the data, do you still have some additional freedom left?
Yeah. So I mean, exactly, sort of understanding the freedom is exactly what I will talk about in a second. Okay. Yeah.
Okay.
Sorry. So the first theorem, yes, we can do it. That's essentially the theorem. And let me tell you how you do it. So again, everything reduces to understanding how to glue along one outgoing null hypersurface, a Minkowski sphere, to a Schwarzschild sphere. So we parameterize this outgoing cone in spherical symmetry by V being between Z0 and 1, and we set omega equals 1, which you can think of a gauge condition. So we impose actually that the DUR here is actually large. So this means that dVr and delta R here actually is small. So you can think of this as a short pulse. So you just send in a big short pulse. And then you just then you use the amplitude of phi. You can modulate a little bit to exactly have that the amount of Hawking mass you put in is exactly the amount of Hawking mass you want to put in your black hole. And so this is just an application of the intermediate value theorem. So this is like the first thing you would try, but this is not enough, and it doesn't work because of the following, namely that the wave equation for phi is in fact a transport equation for transverse derivatives along this outgoing cone. So it means that transverse derivative du phi here, they're transported and sourced by phi along the outgoing cone. More precisely here, the dv of du phi is exactly this. So a generic profile of phi along sort of a generic short pulse here can only ever achieve that du phi is equal to 0 there or equal to 0 there, but not both being 0 at the same time. However, to do the gluing, you want that du phi is equal to 0 here and du phi is equal to 0 there at the same time, and moreover also higher derivatives. So this is sort of a constraint. So this is why, let's say, sending only one short pulse doesn't work, doesn't do the job. And so the idea is actually that we look at a collection of short pulses, each of which have amplitude alpha, and we make a scalar field ansatz in which the field along the scalar field along this outgoing cone is the sum of such disjoint short pulses. And the Hawking mass condition that we send in this amount of Hawking mass now is satisfied for this alpha, which I now think of as a vector, the vector of amplitudes living on a topological K-sphere. And it turns out that the antipodal map sending alpha to minus alpha leaves geometric quantities invariant, R and omega invariant, because the energy momentum tensor has quadratics, is quadratic in phi. So because all of them are disjoint, sending phi to minus phi actually does not change the Einstein equations. So this means that the geometry remains invariant, but the sign of the scalar field changes. And in fact, you can prove that if you set all transverse derivative of the scalar field to be equal to 0 there, then the map which sends alpha to the value of the transverse derivative there is an odd map. And then you can use the Borsag-Ulam theorem, which is a sort of a generalization, like a rather non-trivial generalization of the intermediate value theorem, which states that then there exists one alpha star on the sphere such that all of them are equal to 0 identically. And so we get away actually with a rather, in my opinion, cheap or soft argument to prove that it is possible that all of that k many of the transverse derivative are equal to 0 there and equal to 0 there. So this is essentially the idea of the proof. And this also extends to the Einstein-Maxwell charge scalar field model, in which case it's a little bit more complicated. But the idea is essentially that we do this iteratively. So first, we glue a part of Minkowski space to a part of a Schwarzschild horizon, just the way I just told you. So then we get this part, and we get this Schwarzschild apparent horizon here. And then later we do this, we glue an outgoing Schwarzschild cone, or like sphere here, along this outgoing null hypersurface to a extremal Reissner-Nordström event horizon sphere there. So I should mention that there's a certain Poincaré obstruction, namely that that the mass is fed or is sourced by dv phi squared, and this is just again this just comes from the fact that the energy momentum tensor is of size dv phi squared, but the charge is only sourced by phi times dv phi, and this has to do with that the Maxwell's equation. They are, if you go back to the systems of equation here, that this is only phi times dv phi, and the charge scalar field energy momentum tensor is actually d phi. So this means that if you do like a short pulse, meaning you go to very high frequencies, like in very small scales, then actually this norm will always be bigger than, or like this value will always be bigger than this value, because sort of higher derivatives become higher. So this means the short pulse cannot produce an extremal black hole. And in fact, in our solution, we cannot do like a short pulse, but sort of everything has to be at frequency scale 1, let's say. Okay.
But just to understand, so that you have k pulses. So
yeah.
Does it matter what is k, or?
No. So the point is that, okay, if you want to create an example which has ck regularity, so it's k times differentiable, then you need like k pulses. So we don't, in fact, in this matter model, we don't have an example which is C infinity, but okay, I mean, there's no, but C 100,000 is, we can do, exactly, yeah.
I see.
Yeah.
Can you say what is the physical process? Suppose that I wanted to actually do something like that with light, representing the scalar field. What do I need to do to create these pulses, and how would they propagate in real space?
Well, I mean, what you want to do is, well, you set up a collection of pulses, but you have to tune them exactly.
Yes,
and
but
then
what do you mean by a pulse? Is it a spherical wave that has a specific duration and starts from a specific distance away from the would-be black hole?
I mean, yeah, what you do is you send in exactly spherically symmetric pulses to the interior, and then you let them interact. Exactly, yeah. I mean, that's what you do. But you have to send them in sort of you have to send them in a specific way, such that actually there's no backscattering from the event horizon, in the sense that the exterior after some finite advanced time, sort of that is the difficulty of this whole procedure, that the exterior after finite advanced time is isometric to extremal Reissner-Nordström. In other words, that everything you send in will actually be eventually swallowed by the black hole. Everything you send in will be swallowed. So this is sort of the difficulty in some sense. And
the first one that you send in just collapses and then expands, right?
well, I mean,
Because there's no horizon. So
okay, but it expands locally, let's say, but you will never reach it. It will, because the other one's coming in later, and they're coming in sufficiently fast that actually they also the first one will never go to null infinity.
and these waves, they interact with each other?
Yes, of course. Yeah, they interact. Yeah.
And how is this interaction taken into account in your picture?
Well, I mean, the point is that we don't. So the point is that they interact here, but we don't care about this because we know that by the domain of dependence property, once they interact, like how they interact inside the black hole, I don't care and I don't know, and that's a difficult problem. I agree, but this is not the problem I want to solve. What I want to solve is just that they don't escape the black hole, and this is something I can prove. Yeah. Okay. Yeah, so sort of the gluing method allows us to construct further interesting behavior. So one theorem we can prove is there exists black holes without trapped surfaces. I have to see the time. Oh, I'm actually quite slow. So there exists black holes without trapped surfaces. So they look like this. So this means there's only, actually the event horizon is only a marginally trapped surfaces, but there's no trapped surface anywhere there. And here something important, I think, or something nice comes in, is that, in fact, if you have trapped surfaces in your space-time, then you can apply Penrose's incompleteness theorem, which states that any perturbation of the space-time will also have, or like of the initial data from which the space-time arose, also has trapped surfaces. So this means that incompleteness is a stable property once you have trapped surfaces. So if you have a sort of a non-trivial black hole region with trapped surfaces, then small perturbations thereof also mean that the black hole region is stable. However, if you don't have trapped surfaces, then this argument does not apply anymore. And the Penrose's result does not guarantee the stability of the black holeness of such solutions. And such black holes could be natural candidates for critical solution in the sense that they lie on the black hole formation threshold. So now we enter a new chapter, which is sort of the chapter of critical phenomena and gravitational collapse. So there's this nice paper by Gundlach and Martin Garcia where you can read sort of a lot of state-of-the-art what is known about critical phenomenon. But the basic question in critical phenomenon is sort of understanding the following cartoon picture of sort of the moduli space of solutions. So we have in the interior the Minkowski spacetime, which is like empty space, and then a ball around it where we have all solutions which disperse back to Minkowski space. If you look at matter models which allow for stars, maybe you want to call them geodesically complete or geodesically future solutions. And then you also have sort of those solutions which form black holes. And in moduli space, sort of the threshold between is called the black hole formation threshold. And the natural question is what actually happens on that threshold and what objects live there. And this is typically studied by looking at an interpolating family, interpolating between Minkowski space and a subextremal black hole. And then once you hit that threshold, you call that the critical solution. And there has been very famous numerics for the Einstein scalar field in spherical symmetry by Choptuik. And these numerics are predicted that there is a critical solution on that black hole formation threshold. And the numerics also suggest sort of in the case where you allow for star-like objects that there indeed exists star-like objects on that. But all of those results are of numerical nature, and it's a very interesting problem and open problem to make any of those numerics rigorous. So this is sort of the let's say the traditional picture of gravitational collapse. So let me give you another result. And for this, we look at a different matter model. And I can also tell you why. Okay, we look at this matter model. It's called the Einstein-Maxwell-Vlasov system. So this models a self-gravitating charged plasma. So these are sort of, yeah, exactly. So I should also mention that in this matter model, we can also disprove actually the third law. But this is not the goal of this result. And here the result is as follows. This is from earlier this year. There exists a smooth one-parameter family of solutions d lambda, parameterized by lambda, and a critical value lambda star, such that if lambda is smaller than lambda star, the solution disperses to Minkowski space and no black hole forms. If lambda is equal to lambda star, an extremal black hole forms. And if lambda is smaller than lambda star, if lambda is bigger than lambda star, a subextremal black hole forms. So this means there exist extremal black holes on the black hole formation threshold. And we call this phenomenon extremal critical collapse. So looking at the Penrose diagram, maybe that's easier to visualize even than a collection of scalar field, and where we have this Vlasov field. So the Vlasov particles, so in the case lambda is smaller than lambda star, the Vlasov particles, they come in, or like the fluid particles in some sense, they come in from infinity, and just because of the compactification of the Penrose diagram, it looks a bit awkward. But you should think that the radius of sort of those particles is equal to infinity as they come from past time like infinity. And of course, they're massive. So this is why they have to come from I minus. And then they come in, then they interact with each other, and they are repulsed due to their angular momentum and also due to their repulsion of the charge. They're all charged the same. They all have the same charge. And then they're repulsed again to infinity, and then they go out to plus infinity again. So nothing interesting happens. They interact, but they go all the way. They go off to infinity again. So there's full dispersion. I should say that actually the exterior of them by Birkhoff has to be a family of the Reissner-Nordström solution, which in this case is actually part of super extremal, and the interior is Minkowski. And exactly at lambda equal lambda star, there is actually an extremal black hole which forms. So they come in, they come in, and turns out that the exterior of it will be isometric to an extremal Reissner-Nordström, and there exists event horizon. So this means that they interact with each other and form an extremal black hole. And once lambda is bigger than lambda star, they form a subextremal black holes, and then you have a region of trapped surfaces. And you see that extremal black holes are in fact the only black hole solutions, I should maybe stress that again, which can possibly arise on the threshold of gravitational collapse because they contain no trapped surfaces or like trapped spheres. If they did, then okay, they would not be able to, you would not be able to perturb them away to get the dispersive solutions. Okay, so this is the picture. So what we proved is that there is a different way from Minkowski space to a subextremal black hole. So there's a different way leaving the dispersive region to the black hole region where you hit on the threshold an extremal black hole. Okay. One way to visualize this, I think, is to look at the quantity 1 minus 2m over r along a late ingoing cone. So you should think that I plot 1 minus 2m over r along a cone of this type, which is like late ingoing. Okay. Okay. What happens is that if that quantity is negative if you have the trapped sphere. So in the case of lambda equal to 0, you have Minkowski, there's nothing wrong. If you now sort of are close to lambda star, but still less, then actually this 1 minus 2m over r bends down and it almost becomes 0. And exactly at lambda equal lambda star, you have an extremal black hole. And if lambda is bigger than lambda star, you have a sub-extremal black hole. And you see that you have sort of here one root and here another root, which corresponds to the event and Cauchy horizon, respectively. Sort of, okay. So, okay, how much time do I have left? 5 minutes. I would like to actually mention this because Amos is in the audience. Is that
you can take a few more minutes.
okay? Is that actually our proof is based on a desingular? So it's based on a desingularization in some sense of a singular toy model, namely the Einstein-Maxwell charged null dust model. So this is a model which, well, as the name says, sort of couples charged null dust to the Einstein-Maxwell system, and there's this form. And this is not a well-posed model, and it's interesting to understand how it is well-posed, but an explicit singular solution can be written down in terms of gluing an ingoing to an outgoing Weidier solution. For free functions, sort of var pi, which you think of the Hawking mass, or like renormalized Hawking mass, and Q in. And so you can write down explicitly sort of this Weidier solution, and this will solve actually that system if you set K to be this quantity and rho to be this quantity. And this was done by Ori. And actually, there has been a lot of confusion about this model beforehand, where they didn't even solve the right equation. So Ori sort of had now sort of formulated the correct version of the equation. And yeah, so you can do this. And now you observe that actually there's a specific radius. If the radius is equal to this quantity, then what happens is that K, the momentum, becomes equal to 0, and rho blows up. So you cannot sort of continue that solution further for R less than RB. And Ori's interpretation is that once an ingoing fluid trajectory hits that bounce hypersurface, it has to change direction from ingoing to outgoing. And you can motivate this also by looking at sort of the massive case, in which case sort of you see that the limiting procedure of mass going to 0 should actually be in which sort of you glue an ingoing fluid trajectory to its outgoing version. So in the case where this bounce hypersurface is a space-like hypersurface, you're in business, because now you can do an explicit surgery procedure by gluing an ingoing fluid solutions to an outgoing fluid solutions, and there's never any point in which you have to study the interactions of ingoing and outgoing one. So you can do this. However, I should still mention that sort of the metric and the solution are still rather singular here. So I want to actually produce an example of smooth extreme critical collapse. But nevertheless, sort of this is important here. In the case of the time-lag, if this, for instance, were time-lag or doesn't have any causal character, then you'd have to study the ingoing interacting with the outgoing, in which case you cannot write it down as a Weidier solution. And okay, this is a very open problem how to do this. And however, I should say that sort of the space-likeness of this hypersurface is a teleological assumption, which you cannot essentially assume on the level of initial data. So nevertheless, sort of in Ori's model, in the charged null dust model, we prove also extreme critical collapse. And in fact, we can prove that you have these type of behavior happening. And the proof idea is, instead of prescribing sort of the free function as in Ori's models, we directly prescribe sort of the geometry of that bounce hypersurface and deduce everything from there. So we start from what we want to end up with. Okay. And okay, so maybe I'll skip over this. So the Vlasov case, you should think of a desingularization of the proof of extreme critical collapse in Ori's model. I think this is a great model to understand this, but of course it has the property that the solution is not smooth across the bounce hypersurface, and in general the model is not well posed for generic initial data. So this is why we wanted to prove it in a smooth model, or like in a model which is well posed, where you have stability of Minkowski space and so on. And this is why we study it in the Vlasov case. And I don't want to go into details now, but I want to say that our result is a desingularization of the model of the result in Ori's model. But here we actually also have to use fundamentally the angular momentum and the repulsive angular momentum of the fluid of the Vlasov particles. Okay, So this is maybe all I wanted to say. I should say that it would be also nice to prove this extremely critical collapse for the Einstein charge scale field model. There's some mathematically technical issues which are difficult to resolve, so we don't know how to do this, but I think maybe in the future we'll be able to do so. Okay. Let me now come sort of into the business of the conjectures. So the first conjecture I want to state is that we conjecture that extremely critical collapse is a stable phenomenon. So this means that we believe that actually we constructed now this one curve interpolating from Minkowski to a sub-extremal black hole. So if you believe if you perturb this curve, then again, well, we know then again you will hit the black hole formation threshold at some point, but at that point where you hit it, you again have an asymptotically extremal black hole. However, this is also non-trivial statements about the interior structure of black holes. And there's a further difficulty, namely the Aritakis instability associated to extremal horizons. Let me, however, give you a recent result, which we put few weeks ago on the archive, where we prove actually that extremal Reissner-Nordström is codimension 1 stable, the typo. Meaning that, so you should interpret that actually there exists sort of a codimension 1 submanifold in the moduli space, along which you will always asymptotically converge to extremal Reissner-Nordström. So it is in that sense, it is from that perspective it is as stable as, for instance, Schwarzschild is in that, or any fixed parameter ratio E divided by M is in that matter model. I should also mention that you also have, in addition to this stability, you also have the Aritakis instability, but the Aritakis instability is much weaker than sort of the metric stability. So both go in hand and both are compatible. Yeah, so what about the vacuum case? Far less is known about vacuum, and even the third law has not been proved. So we conjecture, well, that already restricted to vacuum, the third law of black hole dynamics is false, in the sense that you can get a Schwarzschild to apparent horizon only for space-time later to form an exactly extremal Kerr event horizon. So in vacuum, we know that we can do this if the Kerr parameters are much smaller than 1. So we can create a very slowly rotating Kerr event horizon. But the general case where A divided by M is equal to 1, we don't know. And in terms of extremely critical collapse, in principle, also this extremely critical collapse, the stability of it and the revised picture of the moduli space can also be conjectured to hold true in vacuum, with extremal Reissner-Nordström replaced by extremal Kerr. And however, this is a difficult problem and also relates to understanding the codimension stability and stability of extremal and near extremal black holes, the sort of nonlinear ramifications of horizon instability associated to extremal Kerr, which are even stronger to horizon instability and an extremal Reissner-Nordström. And I would maybe mention there's a nice essay of Mihalis Dafermos on the stability problem for extremal black holes, and this appeared, I think, in some conference proceedings like a couple of months ago, in which he actually sort of describes the stability problem for extreme black holes. And on that note, I'd like to thank you for your attention.
Thank you, Christoph. Great, so thanks for a very interesting talk. We had quite a lot of questions, but we can take a couple more.
I would like to ask a question, please. Just a minute. Yes. Maybe even a few. The first is that the third law for black holes is not isolated from the rest of physics, because by now, of course, we know that black holes are thermodynamic systems, just like any other thermodynamic system. And I think that you're not claiming that the third law doesn't hold in other physical systems, only in black holes. And that would be very strange. So that's comment number one. Comment number two is about the formulation of the third law that you used. You used the formulation that it takes infinite time to reach zero temperature or infinite number of steps. But there's another formulation which is more widely used, or maybe it's equivalent, that says that at zero temperature, the entropy goes to either 0 or some universal constant. And you didn't mention at all this other formulation. Finally, a question related also to previous questions. I was trying to understand in what way was the process that you described different than processes that were described in the past. I believe you were using spherical matter, infalling spherical matter. And as far as I could tell, the only difference was in the amount of smoothness. Maybe instead of being smooth, it now was smooth only up to 100 derivatives. Maybe that's what I understood. So is that the case? Is that the difference between your thought experiment and previous ones?
Yeah,
Thanks.
for those questions, I think I noted all of them. So let me first answer the question about the third law. So first of all, I would like to mention that I disprove, and I don't only claim it, I disprove the conjecture I stated. There are many. Okay, so this is a conjecture about the classical dynamics of so this is a conjecture about the classical dynamics of the Einstein matter system, and this has a precise formulation, and this is disproved. Whether you want to interpret that, whether you want to say that this disproof corresponds to some other disproof in some other theory, now, okay, this is not what I claim. I claim that this formulation is the one I disproved. If you call this, if you want to say, well, this is now equivalent to disproving this other theory, this is not what I claim. This is maybe some other people what they say, and this does not have a precise mathematical formulation. So this is the only thing I'm saying. Regarding the formulation of the third law, indeed, there is the other formulation, what you mentioned, in which case the claim is that the entropy becomes equal to 0 once kappa goes to 0. So this formulation was never entertained in the black hole case because it is trivially false by the existence of the extremal Reissner-Nordström solution as even sort of so in that sense, this formulation was never entertained in the black hole case, and okay, I think you can even read this in maybe Bob Wald's article or maybe
If you consider not going to 0 but going to some universal value, then it still generalizes.
I guess it would still generalize this, but okay, now it's also disproved. So okay, I mean, yeah. Now then we also disprove this formulation, but let's say in the literature it was never really entertained, and this was the formulation which was entertained exactly for the reason that the other one was sort of trivially false according to them. And the third, what was the third question again? Was about
the third question was what was different in your thought process.
So actually so essentially nothing is different. I think that the point is that nobody really had ever, I think this should have been able to observe. I think that sort of things which people were able to do back in the days, they should have been able to see this phenomenon happening. Yes, I think, and in some sense, it's very unfortunate that Israel was so close. In some sense, maybe Israel was one of the people who was the closest person to disproving the third law. And in fact, I mean, if you read his articles, there he understands a lot about sort of full global dynamics of the Einstein equations. And I think there was maybe just some indoctrination that led him that somehow it should be true. So he actually motivated sort of, there's this paper in which they even where they produce counterexamples using massive dust shells by Faryuga Hadje, and he's acknowledged in that paper, and he actually told them this problem that you should disprove the third law using sort of irregular matter models. And somehow, okay, for some reason he had this idea that it had to be true. So in some sense, I think it's a historical coincidence that maybe the sort of, I don't know, I mean, maybe the best person on this to work on Israel had sort of this idea that it had to be true. And yeah, so yeah, maybe that's my answer. Yeah.
Okay. More questions?
So I have a question. This is a little bit related to what Barak initially asked or commented. how do you think, or do you think that this can be generalized to asymptotically ADS geometries?
Yes. I mean, that should not be an issue. I mean,
But
I think
then-
that's
Okay, but then you, I mean, if you believe in the holographic duality, wouldn't this imply that you don't have the third law in thermodynamics of large N field theories?
I don't believe in this holographic duality. So no, I mean, okay, if you sorry, maybe that's no, but I mean, okay, you can now sure what it means. I don't know. Yeah, I mean, this is a very precise mathematical formulation. This theorem, I can also prove it for asymptotically ADS spacetimes, but we can also do it. Yeah, if you believe some. Now you can, of course, entertain your favorite high energy, your favorite theory, and draw some conclusions, but that's not what I'm doing. Yeah.
Thank you.
You're welcome.
I have a comment, maybe. First of all, thank you for this very interesting presentation, very interesting result. But if I'm looking for a way to justify Israel's statement, it might be on a terminological sense. Somebody could say, so the crucial issue, maybe the crucial mistake of Israel is that he presumed that in such situations, the apparent horizons should be connected. And in your counterexample, it is disconnected. You have two disconnect apparent horizons. So one could ask on a terminological level, is it the same black hole in a sense? Is it an evolution of the same black hole, or rather an original hole, a black hole that has been swallowed by a larger black hole, which turns out to be extremal? So I believe we could play a little bit with at the terminological level to try justify some of Israel's work.
Okay, I see what you're saying. Yeah. So you're saying that in his sort of in his case, because the outer apparent horizon is connected, you think of it as one black hole, whereas in the case I presented, you think of it as sort of two different black holes. I guess. Okay. Yeah, I can see that. Even though, of course, taking the definition of a black hole being the sort of the complement of the path of null infinity, sort of the modern definition, of course.
Yeah.
This is a connected component. So, but yeah, I can see what you're saying. Yeah, I can see that. Yeah. Yeah, I think that's a nice way of maybe also reading.
So the event horizon is a teleological concept. So in this, can you go back to the previous one?
This one?
In this one, the original event horizon wasn't an event horizon at all. So
Yeah, apparent horizon.
black hole, and the original one was an attempt to create a black hole, and turned out that it failed. So there is some freedom in the to define what we mean by evolving black hole. So
I think that actually, I mean, the sort of reading I studied his paper carefully, exactly, because I know he's very strong and he has done incredible things also in strong cosmic censorship, which I've started off my PhD in. So I think that, okay, I can see what you're saying, but I also think that sort of this implicit assertion sort of is essentially that.
yeah, I agree. I agree. That was his mistake.
Yeah.
Yeah.
But yeah, I see what you're saying. Yeah. Yeah.
Okay.
I'm happy to that. Yeah.
I would like to comment on what Amos said about the connectedness of the outermost apparent horizon. I agree that in these examples, it is disconnected, but I think the notion can be slightly generalized to make it continuous and connected in a way that if you consider not only surfaces which are marginally trapped outgoing, but if you consider also surfaces which are marginally trapped ingoing, then
all of them are.
All of them are
sorry. All of them, the ingoing the ingoing second fundamental form, if you want, it's always negative. Yeah, it's always negative trace in some sense. I mean, the Einstein equation preserved this criterion. Right?
I wasn't talking about the ingoing second fundamental.
Oh, sorry.
Form. I was talking about a way to generalize the picture that you showed in such a way that the apparent horizon would be continuous. And that would be if you consider also the bit that connects, the missing bit that connects. If you show your picture again, you see you can connect the two black parts by a bit, which I think would be kind of marginally trapped, but kind of in a negative way. So I think this phenomena is completely analogous to the fact that maxima of functions, say in one dimension, can disappear only in pairs. Only a maximum can disappear against a minimum, okay? So maximas of functions under continuous deformation of the function can disappear, but only in pairs. Similarly here, what you're looking at, I think, is the function R defined over this two-dimensional, is it R? Yeah, I think so. Over this UV plane, there's a function R defined, which tells you whether these points, these surfaces are marginally trapped or not.
It's actually DVR, but yeah, sure.
I believe this notion of outer apparent horizon and marginally trapped can be generalized in such a way that it is continuous.
No, I mean the point is that okay, the outermost. I mean, okay, I disagree with that. DVR. So the question is, so that the apparent horizon is characterized through the statement that DVR equal to 0. So the outer expansion is equal to 0. Okay, so it's the level set of that function. Okay, and the level set of smooth functions that can actually, and the level set of smooth functions can jump, I mean, discontinuously, and this is exactly what happens here. That here you have that DVR is identically 0 here, but there's an open neighborhood around it where it is actually positive, except of course for that line where it's equal to 0.
But what about places where the UDR vanishes?
D by du of R.
D by du of R.
D by du of R is always negative. This is an assumption which you pose on your initial data that you have to, otherwise, okay, this is like the no path trapped surfaces, right? Du of R is always negative and is actually propagated by the equation to be always negative.
Also in this region interconnecting the two, I'm talking quite intuitive. I'm not certain, but
no, it's a very easy proof you can do that. A consequence of Reissner-Nordström's equation that if you impose d by dr being negative on your initial data everywhere, then it is negative in your future evolution. So you don't impose path trapped surfaces on your initial data, which is a very natural assumption. Then d by du of R is always negative.
Okay, so perhaps this is not the generalization that I need, but I insist that I had some generalization, but I cannot reproduce it right now, so I would need to refresh
it. Okay, yeah, thanks. Amos, do you have another?
Oh, Amos, do you have another question? Your hand is up.
Oh, no.
Your virtual hand. Okay. So if there are no further urgent questions, let's wrap it up and thank Christoph again.
Thanks for having me. It's a pleasure and great questions and comments. I really appreciate it.